Welcome to Soil Structure Engineering Problems YouTube channel. So as I have promised, this is gonna be a video to cover the topic of post-processing. In our problem, we have been setting up before for a group of 9 piles on 2 layers of soils. So when we are doing post-processing, we need to be careful that we understand exactly what we are showing as a result in our models. So in this case, let me just start with showing the geometry. This is the geometry, and I will add the layer that is hidden at the moment. So in this problem, and as we use this section plane to see the group of piles and the soils, I have been calculating or setting up, several post-process results. The first one is the deformation of the group of piles exclusively. So I have selected only the group of piles to see the deformation in the Z direction, which is the vertical direction in my problem. So in this case, this is useful because if you are interested in the study of the settlement of the foundation, this problem is telling you that the deformation or the settlement at the tip of the pile, as you can see in blue in here, is about 17 millimeters, and the cap have the maximum settlement equal to almost 21 millimeters. Another thing to take into consideration is, of course, this is based on a model that is linear elastic and isotropic. So this is an elastic deformation that will be recovered in our model if we remove the loads. And what's happening in soils is actually the opposite, because we don't usually recover deformation in soils. So this model has limitations, so don't forget about this. But in terms of post-processing, this is what we can show, for example, in terms of deformation of the piles. If we are analyzing lateral displacements of the group of piles, we can show as well, simply choosing the option of showing the deformation in the X or Y direction. So this is quite simple to do. There are some things that maybe are useful to discuss in here. So as I have shown the other day, in the previous video, you have several options in here to try to show the results in different ways, using contour bands, iso lines, or the smooth that I prefer in this case. Another useful thing is to see the undeformed structures or undeformed geometry. You can do that showing in here or clicking in here, show on the form model. You can show or not the elements. Sometimes it's useful, sometimes it's not. I have decided not to show in this case. And you can add as well, as I said, the deformation. So you have something to relate them, with the result. In this case, it's very clear that the deformation was produced mainly in the vertical direction, and that's it basically in terms of deformation. But I will take advantage as well to show you that you have these two buttons in here, maximum and minimum, where with these two you identify the maximum and minimum deformation, in this case in the Z direction, and you have as well this button probe in here, which is basically a tool to to identify manually the values of the post-process, in this case deformation, at every point of the geometry. So it could be useful in some cases to identify points or areas of concentration of stresses, for example, that we can see in a few minutes. So for the moment I will deselect all of this. So let's go to the next one. I have been setting up the equivalent stress. So once you select this option of equivalent stress, the main thing in here is to understand what is this equivalent stress in megapascals. So let me just identify in here. So I will share with you this slide where we have the definition. Sorry for that. Okay, I will keep it like this. So in here we have the definition of the equivalent mole misses from the manual of Axin workbench. So basically the equivalent stress is a positive stress because it's an expression. This is a square root of this expression inside the brackets. So where you see sigma 1, sigma 2, and sigma 3, and all the stresses are square and divided by 2, and after, if you apply the square root, of course, you will get positive value for this stress. And the stresses inside the brackets are the principal stresses, so you have to remember the definition of principal stresses. So in general, you have the stress tensor that is represented in here by this figure at a point of the soil, for example, where you have axial stresses and shear stresses. But if you rotate this element, this cube, this infinitesimal cube, until you reach a certain position, you will find the directions and the values of the principal stresses. So the principal stresses are the stresses, the maximum, median, and minimum stresses that you find in perpendicular faces of a cube and where the shear stresses are equal to 0. So they are particular axial stresses at particular directions on the planes of an infinitesimal cube you can define at every point of the soil mass, for example. So once we understand what we are showing as a post-process, we can arrive to right conclusion. So this stress is always positive, and this is the distribution of the values for the loads and for the properties of materials and restrictions, and we have defined in this problem. And remember, this is just linear, elastic, and isotropic. So again, we can use the minimum, maximum proof, whatever you want to define, to find the difference location for these values of the elastic, of the equivalent stress, for example. The next one, shear stresses, for example. Shear stresses can be shown in every direction, because remember that the shear stresses, in here I have them. So the shear stresses are part of the stress tensor, as you know, the stress tensor that can be represented by this matrix or can be represented by this cube with the axial and shear stresses. So the shear stresses are symmetric in the stress tensor. So we have three components of the shear stresses in the XY direction, XZ direction, and YZ direction, basically. And all of them can be shown in the software. So in this case, for example, I'm showing the shear stress in the XY direction. So you choose this when you set up the post-process of your stresses. But you can show as well the YZ direction and the XZ direction. And you see these two are very similar, and this is a little bit different because this problem, of course, is three-dimensional, and in the horizontal direction, Y and Z, things will happen more or less in the same way. But in the other direction where we analyze the Z direction, the vertical directions, the values will be different, of course. So you have every component of the stress tensor in this post-process if you want. Because the stress tensor, as you know, includes as well the axial stresses in the X, Y, and Z direction. So you can show these results as well. For example, I have set in here the normal stress, which is the axial stress in the X direction and in the Z direction, to show the results and the distribution. And in these cases, as you see, the stresses are positive and negative because they are not principal stresses. So they have as a difference with the equivalent stress, positive and negative values. So in the post-process of the stresses, then using this software, you can show every component of the stress tensor, so you have a clear idea about the distribution of stresses in every soil mass or every mass of a structure you are studying. Again, you can use to identify the minimum, maximum, and you can, you know, label any particular point to see the values of the stresses at that particular point. What else? So you can, as well as I said, show the maximum, median, and minimum principal stresses. So you can then see as well this component of this tensor when it's rotated in the direction of the principal stresses. So sigma 1, sigma 2, and sigma 3 can be shown. Usually we say that sigma 1 is the maximum principal stress, sigma 2 is the medium, and sigma 3 is the minimum. Good. The other thing I wanted to show you is the possibility of using stress tools. So you basically go to solution and you have stress tools in here, the toolbox. So the stress tool is in here. This is the option. And in there you can select different options in terms of what to calculate as a safety factor. For example, you have these 4 options for maximum equivalent stress, maximum shear stress, maximum tensile stress, and more Coulomb stress. So what we need to be sure is we understand exactly what we're showing. So in this case, the maximum equivalent stress, and if you click in the safety factor, you see that the safety factor around the group of pi is not so good, because the safety factor should be over 1 to have certain safety in terms of the stresses. And in this case, the average is 0.13, almost 0.14, but it's very, very low because we should be over 1 to be safe. We see that the majority of the mass of the soil is around 1, and there are some areas with better safety factor. But what we need to understand here is what exactly mean the safety factor, because this is for the maximum equivalent stress. So what the software is doing here is comparing basically the equivalent stress we can see here, this equivalent stress with the maximum tensile stress we can take with our material. And the reason why we say the factor is so bad, let's say, is because in our soil, if you remember, we have set the tensile yield strength as a 0.1 megapascals and for the second soil we have set 0.2, so very low values for these yield strengths. And the equivalent stress in our problem reach values of around 0.73, so far over the value of the tensile and the tensile strength. And as you see the distribution of values, almost all the time we are over this value, and this is the reason why the safety factor is like this. So of course the safety factor will depend on the property of your material, so you need to be very careful when you choose the property of your material to have a realistic calculation of this safety factor, for example using the equivalent stress. There are other options in here to calculate the safety factor, for example the maximum shear stress. So in terms of the maximum shear stress, if you calculate the safety factor is not good, because basically the software is comparing the shear stresses with the tensile strengths of your material. We have set 0.1 and 0.2 megapascal for these limits, and if you check the shear stresses in the XY direction, it's okay because the stresses are far below the value of these strengths. But if you check in the other directions, you see that the values are almost in every point over those limits, and this is the reason why the safety factor is so bad in these cases. So the important thing then to take into account when you are doing the post-processing is that you understand exactly what you are post-processing. So what you are showing in terms of results, and that you understand that all this result depends on the parameters you have defined in your model at the beginning of the pre-process. So I think this is all I'm going to say in this video about post-processing. So the post-processing is a topic that we can discuss in several other videos, but for now I think this is enough for a first approximation using very simple model like this isotropic, elastic and linear model we have set from the beginning. Thank you very much for watching.